Thanks for attending, and thanks to Sally and John and the seminar organizers. It's fun to get to talk to the broader Stanford community. As Sally mentioned, today I'm going to talk about some really new work. I have a real hard time talking about old work. I have much more fun to talk about work in progress or new work. So I'll talk about two papers today, one of which was accepted last week, and one of which is we're currently working on revisions to. It's been submitted initial peer review, and we're working on revisions. Hopefully it will be accepted soon. And this is around the general issue of methane leakage and understanding the impacts of super emitters. Okay, so many people suggest or have argued that natural gas provides sort of a natural bridge fuel between the energy system of today, which is 85 to 90% dependent on fossil fuels, and the energy system of 2100, which we hope to be based largely on carbon-free energy sources such as renewables or nuclear. There's a number of reasons for this, one of which it's increasingly important and obvious that this is going to be important, is that natural gas provides extremely cheap, extremely flexible grid support for variable and intermittent resources. So gas turbines are extremely nimble, can ramp up and down very quickly, and can provide this much needed support as wind or solar comes on and offline. This is becoming an increasingly large deal in California, with very steep ramp rates required in the late afternoon as the sun starts to set. Gigawatts of solar goes offline. Additionally, natural gas is very clean burning, very few health impacts and other sort of ecosystem impacts compared to coal. And so where a lot of coal is consumed, let's say in China for power production, or light industry or heavy industry in those regions, natural gas could be a supplement or a replacement for that. And so maybe we think natural gas is a good bet for this sort of 50-year sort of transition period. There's a big challenge, though, which is methane leakage. Methane has a high global warming potential. The newest IPCC physical science basis documents suggest over a 100-year integration period, you have something like a 33 times impact for methane. Over 20-year time periods, it's more like 80 to 85 times impact of CO2. So you really don't want to lose any of natural gas molecules or methane molecules. You want to oxidize them all to CO2. You have a very large distributed infrastructure in the United States. There's about 950,000 wells, last time I looked, that are producing oil and gas in the United States. About half of them are classified as oil wells, but a lot of the oil wells produce gas as well. 2 to 3 million kilometers of pipe, about 2.5 million kilometers of small-scale distribution network, hundreds of thousands of kilometers of large diameter transmission pipe. In connection, so if you view it as a tree, you're gathering gas from a variety of wells, aggregating them into processing points, sending them down transmission lines, and then branching out to all the users. There's something like 80 to 100 million endpoint connections to the gas grid, gas users. So this is an incredibly complex, large distributed infrastructure. Each one of these points can have many possible points of leakage. Each well can have hundreds of possible components, for example. How do we understand the methane leakage problem? And this is just a general framing slide. This was really nice. This diagram was done for us by a professional artist as part of the Novum project. There's a variety of methods to understand leakage that can be broadly classified into top-down methods and bottom-up methods. Top-down methods use, for example, tall towers. NOAA, the National Oceanic and Atmospheric Administration, runs a network of tens of towers across the country, and they'll take samples of air repeatedly, sort of continuous analysis. You can fly airplanes, and people are even doing satellite remote detection. Bottom-up methods involves, sending, let's say, a scientist out to a facility with an analyzer to, let's say, image gas leaks or detect methane concentrations to, for example, count leaking components. The advantages of a top-down source is that you're going to detect all emissions across a given area, and you can cover large areas and essentially integrate all impacts across, let's say, 1,000 wells by flying a perimeter around a region. The advantages of the top-down or the bottom-up methodologies is that you have knowledge of the sources. You're standing there next to the compressor. You know where the leakage is occurring from, and so you get a really nice sense of sort of the vintage or source of the gas. And you can also, there's a variety of methodologies to bag and do flow measurements on these leaks. And so you can basically determine what component is leaking, how much is it leaking. Each of these methodologies has challenges as well. You can imagine if you're flying an airplane, you're going to see all sorts of stuff, like here's a cow that's emitting upwards, and the plane sees the cow as well, if that cow is emitting methane. And so there's a variety of challenges associated with disaggregating these sources. Chemical signatures and isotopic signatures are used to try to disentangle those, but it's not foolproof. And you have to, for top-down methodologies, you have to account for meteorology. So where is the wind blowing from? Where is it blowing to? What is the boundary layer doing? How stable are the winds? There's lots of issues there. Challenges with bottom-up, it's a great methodology. The problem is it's very, very expensive. Environmental Defense Fund has spent many millions of dollars over the last 2 or 3 years sponsoring studies. These studies are very comprehensive, but they tend to still have sample sizes in the hundreds. So they'll visit a couple hundred wells because it's very labor intensive. It doesn't scale very well. Another possibility that's quite an important one is the possibility for sampling bias. So most of these ground campaigns are done in collaboration with operators. And so the kind of, the danger here is that the kind of operators who, when environmental defense comes to them and says, hey, we want to study gas leakage, can we come on site and look for gas leaks? The kinds of operators who are willing to say yes to that are going to tend to be larger, well-organized, have nice environmental controls departments, and be operators who are more likely to be on top of the problem than not. Okay, and so you may have sort of an opt-in or a volunteer bias. There are methodologies that it could be placed somewhere in between top-down and bottom-up that hopefully combine advantages and disadvantages, or combine advantages of both methods. To give you a sense of what this leak might look like, or what a leak might look like, this is a video taken by my graduate student, Jacob Englander. He's actually in North Dakota right now, driving around. Or actually, he just finished driving around. He sent me a text message. He's visiting wells. This is our infrared camera, so this is some video footage taken by Jacob. And this is a tank battery in the Bakken Formation. This is likely holding, some of these will produce water, but these are likely holding hydrocarbons. And you can see that there's some sort of pressure release vent or other failed device at the top of the tank, and this is emitting a mixture of hydrocarbon vapors, methane, ethane, propane, other light hydrocarbons. This is done with an infrared camera. These cameras cost about $100,000. Very expensive, and this would be invisible if you're looking at a normal video. You can't see that. The infrared camera can see the plume. So this is just an example of the sorts of technologies that people apply and what these leaks look like. So what have we learned about natural gas leaks? And this is sort of my one slide summary of where we are in 2016. And this is all based on work that's been done over the last 3 or 4 years, much of it with funding from the Environmental Defense Fund. It does appear quite robust that U.S. methane emissions in general are higher than EPA inventories suggest they should be. Okay, and this was one of the results from our paper in Science. It does look like some, but not all of this excess methane is likely from natural gas sources. Okay. There's been a whole bunch of new studies, probably 20 studies, fundamental experimentally based studies over the last couple of years that have provided a lot of new insight into potential sources such as well pads, gathering and processing systems, pneumatics, compressors. But there's still a challenge in aligning top-down results with bottom-up results. One of the findings from our science studies is that when you go out and do a top-down study versus a bottom-up study, often you'll find more methane than you expect when you do the top-down study compared with scaling up the bottom-up results. A recent, just published paper in Proceedings of the National Academies of Sciences has looked at this. This is an EDF-funded study, and they found that you have to include some measure of what are called super emitters or large emitting sources to get these bottom-up results to align with the top-down actual observations from airplanes, for example. Okay. So this leads to a couple open questions that I'm working on that come to mind. And I'll talk about these today, and they're quite related, as you'll see. Question one is, how important are super emitters in closing the gap between estimates and observations? And to answer this, we'll talk about statistical analysis of existing data sets that I've been working on. And two, how should technologies and policies be designed to reduce emissions from super emitters in particular? And I'll talk about that at the end. It's worth backing up a second and talking about how bottom-up emissions estimates are made by regulatory activities. So, for example, EPA, since the 1990s, has conducted a yearly greenhouse gas inventory as part of the Framework Convention on Climate Change. And in this methodology, emissions are estimated using what's called an activity model or an activity factor model. In this case, emissions in a given sector are equal to some emissions factor EF times some activity factor AF. An emissions factor is a kilogram of methane per unit or per event, so per compressor or per well drilling event or per some sort of activity. This is typically done using taking a mean estimate of, or a mean of a set of samples, and that gives you an average emissions rate for a given piece of equipment. And then the activity factor is the number of units or events, number of devices, this sort of thing. You multiply the two, number of events times emissions per event, number of a type of component times emissions per component, and this gives you an emissions rate. There's a number of possible sources of error in emissions factors, in activity factors. A couple of examples that actually occurred in the last few years. EPA in 2012 released a new version of their inventory where they included for the first time emissions from hydraulic fracturing operations. They estimated the emissions per fracturing operation, multiplied it by something like 8,000 fracturing jobs that they had in their data set. The American Petroleum Institute responded with a document. They said, well, actually, there were 15,000 fracturing jobs in this year, not 8,000, right? So you can underestimate or overestimate the number of pieces of equipment. Another example, we called the regulators in North Dakota. We were seeing tank emissions as we were driving around. We said, how many tanks are there in North Dakota? The answer was, well, we're not really sure. The air quality permits are filed on paper. And the guy literally went to the basement and took a picture of the 6 filing cabinets that contained all of the data. And so they said, somewhere between 2 to 4 per well. No one knows. This is a real challenge. If like, for example, let's say you generate an emissions factor, emissions per tank per year, you ought to know how many tanks there are. And in many cases, we don't. Errors are possible in emissions factor because the average emissions for emissions factors are almost always taken from small samples. So you got to sample 100 tanks, and you get an emissions rate per tank per unit time, for example. I'd already talked about possible bias from operator cooperation. And also because of the small sample sizes, there are few opportunities to see large leaks. And this will motivate the importance of super emitters in generating these emissions factors. These are two probability distributions for leakage rates for two artificial populations that we created as part of our study. Each one of these populations has 1E5 or 100,000 sources in it, which is a typical number for these national level emissions inventories, 100,000 wellheads or something like this. Let's just pretend there's some arbitrary unit of equipment. And these two distributions, which are normal and what are called heavy-tailed, both have a mean emissions rate of 10 kilograms per day. This one is Gaussian or normal. This one is actually what we call an augmented log normal. So this is a log normal mixture distribution. And I'll talk more about that as we get on. But basically, both of these distributions have a mean emissions rate of 10 kilograms. But here the mean is driven by infrequent high emitting sources. That is, this tail is heavy. The right tail is heavy in statistical parlance. And here the average emissions rate is driven by this sort of average normal behavior. In this case, small samples tend to characterize the behavior very well. In the heavy-tail case, small samples don't tend to characterize the behavior very well, and large confidence intervals result. Okay, and so this is just sort of a motivation for one possible error that arises in generating these emissions factors. So this is a collaboration with a couple of great guys. I always want to acknowledge my collaborators, Garvin Heath, at Department of Energy, the National Renewable Energy Lab, and Dan Cooley, who's a statistician at Colorado State University. We wanted to look into, for this study, a number of questions. Are super emitters found in all studies? How important are super emitters to understanding the leakage volume? If you don't catch super emitters, do you underestimate systematically the leakage volumes? What effects do super emitters have on the emissions factors? So if we add them in, do these emissions factors increase appreciably and help close this gap between top-down and bottom-up methodologies? What sorts of statistical distributions can be used to model these leaks? And can we do meta-analysis across previous studies to say something about the prevalence of super emitters? So this is really what we're looking at. We gathered all available estimates. We have 21 studies in our data set over 15 years, about 20,000 observations across these. Every study we could find where the actual recorded volumes for each leak were recorded. Various quantification methods. Direct measurement is the most common, but some of these are reported. So we have data sets from PIMSA, the Pipeline and Hazardous Materials Administration. Federal Pipeline Safety Administration has data sets on all federally reportable leak incidents, for example. But for the most part, these are directly quantified, measured by scientists via bagging or other methodology. We perform statistical analysis using extreme value theory to estimate the properties of the leaks, and we analyze the implications for technology development. We'll skip right to the results. The best way to, it's really hard to, this is 20,000 observations from 15 studies, very different scales, very different sizes, very different numbers of samples taken in each study. Some studies had thousands of samples, some studies had, I think our smallest was 19. We decided the best way to do this was to essentially create normalized cumulative distributions. On the x-axis is the cumulative fraction of samples in a study, 0 to 1, okay? On the y-axis is the cumulative fraction of total emissions contributed. And what we do in order to generate this is we take a series of observations, we rank order them largest to smallest, right? And then we accumulate them here and create a cumulative distribution that basically will increase like this up and to the left as you go from 0% of the fraction of total samples to 1%. And again, moving along the x here, we have anything from 20 observations to 2,000 observations in our smallest and largest categories. As a guidepost, we're going to create a little template here. This is a uniform distribution. If you have a uniform distribution that has every leak is exactly the same size, you rank order them smallest to largest, accumulate them, and you get a 45-degree line. That's easy to imagine. Any non-uniform distribution is always, by virtue of rank ordering them largest to smallest prior to accumulation, is going to be above this uniform line. Any real data set is going to be above that line. Here are two envelopes for normal distributions. This is this one here is with a mean of 100. Actually, those colors are reversed there. Sorry. This is a mean of 100 and a sigma of 10, or a standard deviation of 10. This is a mean of 100 and a sigma of 100. So this is more widely distributed normal curve. This is a very tightly distributed normal curve. We drew 100 different attempts to draw from these distributions, and this envelope basically says, okay, for a normally distributed phenomenon, you're going to see a curve that's going to lie somewhere in this sort of envelope here. A common distribution that's used in previous studies, the previous studies that have noted this super emitter problem have used log normal curves. And so here's a couple of log normal curves as well. Here, this is sigma 3 mean of 10, and this is sigma 10 mean of 10. You can't directly compare the numerical values there because the log normal ones are basically the log of the mean, or the log of the standard deviation. So you can see there with a log normal curve, you can get much more extreme behavior, where when you get to, let's say, 30% of the emissions, you may have something like 70 to 90%, or 30% of the sources, the largest 30% of the sources may contribute 70 to 90% of the total leakage. So what sort of results do we get when we look across studies? I put our little guidepost here in the upper right-hand corner. So this, again, is to orient you to what these sorts of curves look like. And these are the 21 studies, including, as I said, the PIMSA federally reportable incidents, as well as, for example, this one is for abandoned wells. These cover all sorts of sectors or all sorts of portions of the natural gas value chain, from everything from wellheads to distribution systems. underneath our cities. And you can see here that these are quite extremely distributed. One important thing to realize is that actually down here in the very small percentiles, or the very largest sources, they're actually much steeper than the log normal curves, which we'll show. Some of these are actually very hard to fit the small percentile or the very largest observations with log normal curve. If instead of grouping them by study, we say, well, study doesn't mean anything, I'm going to group across these studies and say, what about flanges? What about pipes? What about pneumatic controllers? What about regulators? What about seals, compressor seals, etc.? Many of these types of components were analyzed in different studies. And so 4 different studies, for example, did whole plume measurements downwind of well pads, for example. And you can see here, and so basically what I did for these 20,000 observations, in most cases, the study author tabulated which type of leak it was, which type of piece of equipment was leaking, and so it was up to us to come up with a way to aggregate these reported leaks into a set of sort of cross-study categories. This was non-trivial. Only about 2/3 of the total observations could be categorized into one of these broad classes here. But you can see here everything from abandoned wells to chemical injection pumps to tanks and hatches. They seem to follow this same sort of behavior. So what does this mean in the world of extreme value theory? So we asked our extreme value statistician, or our statistician who works on heavy-tailed events, we said, what data sets in extreme value theory do people actually use? They use things like rainfall events. This is daily precipitation data for 65 years from a weather station in the Rocky Mountains. And so this is precipitation events. Precipitation events are known to be heavy-tailed. Big events are very big and can contribute a large fraction of the total leakage. This is crop loss insurance claims, many decades of data there. This is flood insurance. Purple here is flood insurance claims, many decades of data there as well. Stock market crashes are used as a heavy-tailed phenomenon. So this are the log-transformed S&P 500 crashes over since before the 1930s. And then also there's been a lot of interest in income distribution. So people say income or wealth is unevenly distributed as well. And so these are US 2013 incomes in 26 IRS provided brackets. And so you can see here some interesting things, one of which is that, in this gray line here, these are the devices. So I took all these device categories, which I think are nice because they're cross-study and they're sort of consistent types. So I put them in gray, and so we can compare them here. And you see, especially for if we zoom in, the top 2.5% of emission sources, most of these device categories are actually more extremely distributed than these other phenomena that are studied in extreme value theory. The one that doesn't follow that is flood insurance, which starts about right here. The largest single observation in 60 years of flood insurance claim data was from Hurricane Sandy, which corresponded to something like 20% from one observation, 20% of the inflation-adjusted losses over many decades was from basically one observation, which is why this flood losses is so extremely distributed. So these are quite extremely distributed. The large sources are very important. One important result from our study is what we call the 550 rule. An existing rough definition of super emitters used in numerous places in the literature is that the top 5% of leaks are considered super emitters. So we take that and we look across these studies. For example, we trace up from 5%, and we can see here, in the case of the components, that somewhere between 35 and 85% of the leakage is contributed by the top 5% of leakage sources. And actually, when you look across our 15 studies, our 21 included studies and our, I think we ended up with 24 device categories, on a median basis, the top 5% account for 53 and 57% of the total leakage. That's what that comes out to be. So our 550 rule says on an expected basis, the top 5% of your leakage should contribute more than half of your, top 5% of your leakers should contribute more than half of your leakage, okay? And some of you have heard this is the 1 millionth application of the Pareto principle, or the 1 millionth observation of the sort of the Pareto principle that applies everywhere in the universe. The Pareto principle is often classified as the sort of the 28, or described as the 20-80 rule. So with 20% of the effort, you get 80% of the benefit. In our case, this is more like 2090 or 2095 is really what you should expect for natural gas leakage. So if you could solve the top 20% of the leaks, find them and fix them, you're at least 90% of the way there. An important result, one, is that a lot of people have been fitting log normal curves to these data sets, but it doesn't work very well. These are called QQ plots, or empirical quantile plots. And the results here, basically here, these are EPA greenhouse gas reporting program measured and reported by companies' emissions rates for blowdown valves. And what you see here, this is the model result of what you'd expect if the log normal curve that was fit to this data set held. And this is the actual empirical observation. There's actually 1,000 or 2,000 observations down here. This is what the log normal is fitting to. And you can see here, when you get to the very largest emission sources, the log normal significantly underpredicts what the largest sources should be. So this is why we say, and this holds across all sorts of subcategories that we said, or that we examined. And so this gives evidence for, or support for, what we're calling heavier than log normal behavior. So what are the implications of this? Why should it matter? It's hard to know from the existing empirical data sets what impact this should have. And so the easiest way to do this is actually to simulate. And so what we did is we took two artificial samples of size 100,000, and we create all of these leaks, or we create all of these devices with leaks. And so we know exactly what the population emissions are. So when we go out and we artificially sample them computationally, then we can say how accurate are we. In this case, we have a Gaussianly or a normally distributed population. And in this case, we have an augmented log normal. This is a log normal distribution where some of the emitters are taken out and replaced with heavy emitters to recreate this sort of heavier than log normal behavior. So that's what that looks like. If we, over 1,000 times, sample from this, take the mean and multiply the mean by 100,000 devices, this is a replication of the emissions factor times activity factor approach, what is our predicted emissions going to be? In each case, the actual emissions are given by a dotted line. You can't see it here. And you want your prediction to fall around that dotted line. Okay? And you can see in the case of the Gaussian distribution, you almost always predict the correct value. You can see in the case of the heavy-tailed distribution, more often you underpredict, less often you overpredict. When you overpredict, you tend to overpredict by a lot. This is how the 95% confidence interval changes as a function of sample size. As you increase the sample size, your prediction basically narrows in on what the actual value is. And to get a 95% confidence interval to be a window, it's plus or minus 10% around the actual mean, again, because we know what the actual mean is because we've created the population, you need a sample size of about 40 devices in the Gaussian case. In the augmented log normal, we need to sample over 4,000 devices before we narrow that confidence interval around our mean to plus or minus 10%. So this suggests to us that existing studies don't have sample sizes large enough to begin to understand with any fidelity what the mean emissions rates are. Another important thing is how large of a leak might we actually need to find? Okay? So this is very important because there's a lot of funding going into leak detection technologies right now. For example, ARPA-E, Advanced Research Projects Energy, has an ongoing program to fund leakage detection. Their target was a leak of size, they want you to be able to find a leak of size 1 ton per year, 1 ton of methane per year. If we take those distributions before, but instead of normalizing them on the axis, we have the actual magnitude on the x-axis here. We have the size of leak in kilograms of methane per day and a reverse log scale here. Black is all of our observations cumulated together. So this is all the observations in our 20,000 measurement sample. And you can see here, if we just start with every observation in our data set and we just march upward, we get to 90% of emissions when once we found leaks larger than or equal to 60 kilograms of methane per day. The ARPA-E target of 1 ton per year is about 2.7 kilograms per day. So ARPA-E wants a target somewhere In this sort of range, we're saying that it's about a factor of 25 larger, could actually get you 90% of the leakage. Now, a key caveat here, and we're sure to mention this in the paper, making that claim, you're basically making an assumption that this database of 20,000 leaks replicates in some way the universe of leaks that are out there. That's, of course, an assumption based on all these concerns that we had talked about earlier of sampling bias and things like this. Okay? But this may give you some sense of what sort of fidelity or specificity might you want in a detector. And the answer may be you can get lots of benefit even with only being able to find a reasonably large leak, like 60 kilograms per day. Okay. So what are some implications here? Design of technologies for detecting leaks should account for the size distribution of leaks, right? So you should incorporate these sorts of data sets if you're trying to say how sensitive should my detector be, how small of a leak should I be able to find. Reducing uncertainty to sort of what we might consider to be reasonable bounds is going to require pretty large sample sizes if the distributions follow, or if the leaks follow these observed distributions. Because basically the way our statistician frames it, you need a large number of samples because the few large leaks that can really drive mean behavior don't appear very often. If you have a small sample size, you only see a couple of them, and so you have very little information about the tail. So there's a variety of ways you might go about this. For example, you can try to oversample in the tail, but that's hard when you don't know how to find the tail to begin with. Targets set by funding bodies should align with and include better understanding of the leak size distribution. We are going to open source this data set that we've generated with some effort, so that'll be pretty nice. I'm just going to talk in the last little bit or so about a second question about understanding detection technologies, and we'll do kind of a high-level treatment of this. This is a work that just was accepted for publication last week, and this is a simulation toolkit to compare detection technologies. My wonderful graduate student Chandler Komp was the brains behind this. He's really done a fabulous job here. We created what we call the FEAST model, the Fugitive Emissions Abatement Simulation Testbed. The problem here is that many detection technologies exist and many more have been proposed. Sort of everyone and their cousin has an idea for detector technology. I've got my own idea. That's why I know everyone has an idea who's working in this area. Because if I've got one, then everyone else surely has one. I've got my idea. Everyone else has their ideas. How can we rigorously, fairly, and cheaply compare these different ideas? So I say my detector technology is better. You say yours is better. How on earth are we to know? Okay, so what we've done is we've developed a virtual training ground for these technologies. It's sort of an in silico sort of way to test different proposed technologies. What we do is we initialize an artificial gas field. This is an actual terrain from the Barnett, and so these are the wells in a 5 by 5 kilometer region in the Barnett. We get things like well counts, road distances, and equipment counts and components for this set of, in this case, artificial wells. We initialize leaks by drawing leaks from our real leak distribution data set that we'd previously talked about. So this is leak size and then the prevalence. So most of them are very small, but there's these few sort of outliers. This data set we took from the Barnett to line up with this case study. We can then simulate each of these leaks with a chemically buoyant Gaussian plume simulation methodology. So here's an example of a plume in a heavy wind. And so that's a cartoon Gaussian version of the plume that you guys saw earlier that was being blown, swept to the side. So this is concentration. Once we have that, we can actually simulate every leak for every hour. And then we say, let's go out and pit some of these detection technologies against these artificial leaks. Oh, sorry, actually, not there yet. Step 3, we add and subtract leaks over time. So we have what's called a two-state Markov model, where components, each of the components at a site can flip between leaking and not leaking with certain probabilities. And we include a background repair rate. Here's some results from Jacob's current study where he's going out and repeatedly observing leaks to see how quickly they flip on and off, because this is a real challenge for this modeling effort. We then perform, using this Gaussian plume model, we then perform a 10-year simulation where every hour we draw a wind speed from a wind speed and wind direction. This is the wind rose for the Fort Worth Airport in the Barnett region. So again, we're looking at the Barnett for our first case study. So this is wind speed and wind direction. It's mostly north-south in this case. And then we apply a modeling we model a leak detection technology to fix and find leaks at certain intervals. So what can we show here? So we can compare technologies. In this case, this is our time over 10 years. Each day we simulate. This is what would happen if no repairs were ever performed on the field. Okay, so the leakage rate in grams per second per well would go up. This is what we call our null case, where the probability of a leak being fixed is about equal to the probability of it being generated over any day or any time step. And so the leakage rate tends to creep up and down, but workers find problems, fix them, new problems emerge, this sort of thing. This is what we're considering all the technologies against. When you apply a given leak detection technology against this artificial gas field, the rate goes down and is held at a lower level depending on the detection technology. And we can integrate the value over time, computing, for example, the net costs and benefits for each detection technology, including capital costs, finding cost, repair cost, maintenance cost, and the value of the gas found, and get basically a 10-year NPV, which is positive for 3 of our 4 detection technologies. So one thing that's really nice here, and my postdoc Arvind Ravikumar has spent a lot of time over the last couple of months really improving our simulation of the IR camera in this toolkit, is we can basically artificially, before somebody goes out and let's say put in a bunch of engineering effort to increase the sensitivity of a detector, we can say against this artificial but actually generated using real data, against this artificial gas field, do you actually get any benefit, or are you willing to pay any more for increased sensitivity? Or does that not get you very much because you are already finding all the big ones and the marginal leak found when you improve the sensitivity is small, right? And so we can begin to study these sorts of trade-offs. We're open sourcing it. We have open sourced it. It's available online, the model and all the underlying data sets. So I think a bunch of interesting questions here. We hope people pick this up and use it. How much should we pay for improved precision? Where do we place detectors? How often should we survey? Should we go quarterly? Should we go yearly? EPA is currently working on this question literally as we speak. And it's not clear that much analysis has gone into this thus far, which is a big challenge. So EPA has a proposed methane rule that requires optical gas imaging on a semi-annual basis, that when leaks are found, they're fixed within 15 days, and the frequency of the survey is changed depending on performance. Some really interesting initial results from my postdoc taking this FEAST model and again modeling the EPA methodology. What we see here is, as a function of distance for his very sophisticated infrared camera simulator, as distance increases, the amount of leakage increases at the facility. And as the survey interval basically gets less frequent from quarterly to half-yearly to yearly, the leakage rate goes up. So yearly is worse than quarterly, as you might imagine. But interestingly, a yearly survey at 10 meters is significantly better than a quarterly survey at 100 meters. The EPA regulations specify that you will go out twice per year. Unless this is the case, then you will go out 4 times a year. Unless this is the case, then you will go out once per year. But the regulation, as we read it, doesn't say anything about standoff distance. Okay, so they don't specify this parameter. They don't say you need to get close to the well and look at it. And so we're a little concerned that this could result in sort of drive-by surveys. Hear no evil, see no evil. No problem here, right, as you zoom by, holding the camera out the window. So it's not clear that the science has been done at this point to support crafting really effective regulations. And this is something we're very actively working on with help from the Natural Gas Initiative. In order to support these simulation efforts, we are starting experimentation. So I do have to show my dedicated graduate student, Jing Fan. He's a man of much energy and enthusiasm. Wonderful guy. And then this is my postdoc, Arvind Ravikumar. Here we're setting up, we have actually have permission to release methane, which only took 6 months or so. Amazingly, it actually worked. I was surprised that here I am saying on tape that I'm surprised that they're letting us do this. I shouldn't say that. And so here he's filming with our very expensive camera. And so what we're going to be able to do is control distance and things like this, and basically calibrate our simulation tools to see that we can accurately recreate what these cameras are able to do. It's quite a fun project. So moving forward, I'm really interested in collaborating with new technology developers. Really interested in questions about regulatory design. So how do you deal with the technology side of a regulation like this? We want to work on IR camera testing, modeling, and verification. And in the long run, like I said, I have my idea like everyone else. And so we're interested in using machine learning and machine vision to automatically detect blooms against a changing background, and be able to have a robot that drives around and finds leaks to make it much, much cheaper. So that's it. And I think I'm slightly over, but not too bad. Okay, thank you. I'm happy to take any questions. I'll let Sally drive, and I think we want to emphasize students.
Yeah, students get to go first.
Kareem, you're going to be a student for another few days.
I can ask you a question.
Yes, please.
So for
this is double joke. I get a call on students. I know him, so I can harass him. Kareem, I know you have 1,000 questions. What's your question?
I do. Yeah. First, really fascinating work, by the way, Adam. Thanks for the presentation. For the super emitters, you've defined it as, or one of the definitions is the 5%, like the top 5%, but that's based on quantity, like total amount of leaked methane. Is there an equivalent definition for super emitters based on frequency? So is this total amount like emitted in 1 day, or in 1 year, or in 10 years?
This is excellent question. This is at the forefront of what a lot of people are trying to think about. It's very expensive to go out and repeatedly survey. EDF funded a study where they had a helicopter-based sensor that was on a little model helicopter, a very light, low-power sensor, and they flew the same compressor station 30 times or something like this over 6 days. They just repeatedly flew transects with this. This doesn't happen very often. My student Jacob is going out and visiting the same wells over and over again on a 2-week basis in North Dakota, because that's where he is right now as we speak, as I said earlier. But there's precious little data, at least in the public science domain, about how frequent are these? Do they switch on and off? We were out for a week in North Dakota. We saw leaks that switched on and off. Most of them, I would say, seemed pretty consistent, but we definitely saw ones where a pressure release valve would pop, and then it would settle back down. And then you'd sit there and stare at it for a bit, and it popped again. And you could hear it from 50 feet away. It would psh, and then settle back down, right? And so some of them are intermittent. Typically, the assumption that's made when you go out and sample something, I get this leakage rate, you assume that's what it's doing and it's constant. But
variations, because if it's only part of a process and it's like done during loading and unloading, then that's something that you can fix. But if it's systematic, then you'll need to come up with a whole different solution.
Yes, that's right. And I think the folks at UT Austin have probably looked most into the unloading loading issue. So there's been a little bit of work, but not enough. It's an open question. That's a very good question.
Okay, more students.
I know some of you others, so.
Yeah, be careful. If someone doesn't volunteer, you have no choice. Okay, here's one over here.
Probably going to pick on it anyways.
Yeah.
Figured I'd just volunteer. Have you seen any movement, given that, I guess you can say you somewhat raised the alarm in the fact that the EPA has some percentage that they think the leakage is, and you said, hey, now it's actually higher. Have you seen any movement on the EPA's front, or is it pretty stagnant?
They make an effort every year to incorporate as much of the current science as possible, and in the past year they've actually released a couple white papers for comment on redoing parts of these equations given the new data that's coming out. This was a big motivation for EDF to sponsor these studies. Literally, some of these data points were decades old that were being used year after year because the studies are expensive. So one of the big goals of the EDF campaign was to get more modern information out there that EPA can update. And they have been. I would say in general, they're overworked, understaffed, and
But there have been new rules, right? So EPA has been very active.
Yeah, EPA has been very active, and actually, thank you, Sally. Yeah, I was thinking more about the inventory. So I do know the folks who work on the inventory, and there has been some adoption. The estimated leakage rate is about the same. Things have gone up and things have gone down, but but I think they are actively working on that. There is a whole new suite of regulations going out around the new source performance standards for new wells that are going in or significantly retrofitted wells that are going to require improved emissions control equipment and things like this. And so EPA has been working on that as well. That's a different division than the inventory.
Okay, we'll open this up to anybody. Okay, you got your hand up first in the green sweater.
Is there any possibility of using drones for either the cameras or the detectors?
Yeah, so that's where we want our idea to go eventually, and I would say at least half of the people who are developing technologies think that it's going to go on a drone eventually, because it's so expensive to send guys earning, $80 an hour. These are very remote fields, and so if you can send a drone, yeah, this is where it's got to go eventually. It'll be very cheap, very fast, and very cheap.
Okay, well, okay, we'll go over here.
Is the emission rate in the leak rate in the United States more or less than 1% of natural gas production?
Almost certainly more than 1%.
Is it worse in Russia?
No firsthand experience. I've talked to people who've been there, and the experiences relayed suggest it would be higher, but.
Who's higher?
Russia. But I've talked to someone, and she had been in a Ukrainian gas field before or something like this, and she relayed horror stories. But what is that? That's nothing. I don't know. There's very little study internationally, actually. Very few studies internationally.
We'll take one more question. How about somebody over there? How about in the far section? Yeah, how about you? Yeah, you. Yeah.
What about the liquefied natural gas facilities that are being planned or that exist? Are they evaluated as particular concerns? Are there special regulations because of the extraordinary volumes that are being handled?
No studies have been done that I'm aware of at LNG facilities. There's going to be a whole lot of compression work and things like this going on there. I would assume that because those are large facilities that they'll be relatively well monitored, would be, I guess, my first order guess about things. It's more the very distributed, very diffuse, neglected, old infrastructure. I think that's probably the bigger challenge. But that would just be my guess. No data.
Okay, well, thanks. We're going to wrap up. Sorry, I think Adam.
Yeah, I'll stick around and
to,
stick around and answer any questions. Thanks, everyone.